Alright, so for today's pre-lecture video, we're going to focus, of course, on capacitors, which is the topic of Chapter 24, but I'm going to sort of go through the rules about how we combine capacitors and how we can simplify a more complicated combination of capacitors using the rules of adding capacitors in series and in parallel. So first we have to remember the definition of capacitance because we're going to use this definition when we're doing our work. Basically, when we have a capacitor, its value of its capacitance is the ratio of the charge that the conductor holds divided by the potential difference across the conductors. Remember that the charge here isn't the total charge of the capacitor because the total charge is 0, but it's the magnitude of charge on each of the two conductors that make up the capacitor. So basically, as I said, we want to know how capacitors behave when they're combined. So we'll look at rules for connecting capacitors in series and in parallel, and what that will do for us will help us to simplify combinations of capacitors. So the first thing that we're going to do is look at capacitors that are in series. So the idea of anything that's connected in series is that we have a wire, we follow it from point A, and we come into one capacitor, then we leave that capacitor, we go into another capacitor, and then we leave it. So they're all connected in a line. There's no branching of the wires to go into separate paths. It's just one path around and going from one capacitor into another. So when we're talking about the capacitors and they're connected, there's always has to be some sort of potential difference set up on the capacitors that's going to allow them to become charged. This is really what we have here. We're going to say that the potential difference from A to B is just, we'll call VAB or just V. This is going to be created by a battery. So it's the same as saying we have a battery with a potential of VAB. That's the difference in potential across the two terminals of the battery. Once we connect that battery, what we do is we're giving charge sort of the energy to be able to flow and to move. And what will happen is the electrons will be moving now between the two capacitors, and they will move until there's really sort of no impetus to move anymore. What will happen is the potential difference will allow electrons to gather on one plate of the capacitor and then leaving an excess of positive charges on the opposite plate of the capacitor. And because of the fact that these capacitors are connected in series, we can sort of imagine the excess of electrons moving from here to here, leaving the same amount of positive charge here, and then same thing, the negative charges can move from this plate over to this plate. I'm sorry, but you know what I mean. So basically the idea is because of the way the capacitors are connected and because of the way the charge is going to move, the same amount of charge will end up collecting on each capacitor. So we would say that the charge on capacitor 1 will be equal to the charge on capacitor 2, which is going to be equal to just the charge Q. And so that's what we have to remember when they're connected in series. Now, because they're connected in series, the other thing that we want to think about is what is the potential difference. Now, using the idea that C equals Q over V, we can see that V is going to be related to the charge that's accumulated on each capacitor divided by its own capacitance. So the potential difference across capacitor 1 will be V1, and the potential difference across capacitor 2 we can call V2. But again, in relation to the battery, it has to be true that V1 plus V2 is equal to VAB, or just what we're going to call V. And so now what we have found is we've found the two rules that are going to help us know how to add or find the equivalent capacitance. We say that Q1 equals Q2 equals Q, so the charge is the same across all the capacitors, but the potential difference across the two capacitors here adds and gives us the total potential difference. We're going to use these two facts along with the relationship of capacitance to charge and voltage, and from this we're going to rearrange and say voltage is equal to charge over capacitance. And so this expression right here can be changed to Q1 over C1. V2 can be written as Q2 over C2, and V can just be written as Q over C, and we'll call that C equivalent, because that's going to be sort of the capacitor that will stand in place of the two that are in series. Because the Q's are all the same, we can divide through by the Q's, and we end up with this relationship. And basically this tells us the rules of how we can add the two capacitors to find the equivalent. We have to add the reciprocals, and that gives us the reciprocal of the equivalent. Something that you might not realize at first, but that C equivalent will be smaller in value than any of the capacitors that we are working with. So that's something we can remember if we want to, if we're given a certain, some certain capacitors, but we need a capacitance that's smaller than the ones that we have, we could actually add them in series, and the equivalent capacitance would actually give us a smaller value. So again, just sort of summarizing what we have found for the charge is the same across all our capacitors in series. Our voltage adds across our capacitors in series, and then this leads to the rules for joining them or for adding them when they're in series. We did the example for only two capacitors, but it actually, you can extend it to however many capacitors you have to work with. Now, if we have capacitors in parallel, that's something different. When capacitors in parallel, sometimes the picture makes them look like they're parallel to each other, but the real key here is that we follow the wire, and then the wire comes to a place where it has two different paths to travel through. And then once it travels through, it will actually come back again and join together in a single path. And so the two split paths that we're looking at are the two paths that are in parallel with each other, and that's what parallel means. Again, this represents our battery, and what's interesting about adding capacitors in parallel is when we attach them to a battery, it's almost as if either end of each capacitor are both connected to the terminals of the battery. And so the potential across capacitor 1 is the same as the potential across capacitor 2, which is the potential of the battery, which we're just going to call V. And so this becomes the key to determining how we deal with capacitors that are in parallel. Now, again, we found that all the potentials are the same, and what happens when the charges are distributing themselves, when the battery gives them the energy to move around, is the charge will accumulate on each capacitor in a way to make the potential the same across both of the capacitors. And there's only so much charge that can move around, and so our total charge is divided between the two capacitors. So here, Q1 and Q2 can add up. We can use this idea, and again, the fact that capacitance is Q over V, we can take this expression and rewrite it as C equivalent times V, and then for Q1 we write C1 times V1, and then for Q2 we write it as C2, times V2. Now because all the V's are the same, those cancel out, and I'm left with the equivalent is equal to simply the addition of the two capacitors. And so what we get, we sort of summarize our rules for the potential across the two capacitors, or more if we need it, are the same as the potential across the battery that they're connected to. The charges across the two capacitors adds to the total charge, and then the equivalent capacitance can be found by simply adding the capacitors together. So obviously when we have capacitors in parallel, the addition of them is what we get. The equivalent is bigger than any of the individual capacitors. All right, so here's an example where we can find the equivalent capacitance. So we have these two capacitors we see are in series, but then this branch and this branch, these two branches are in parallel. And so what we want to do first is we're going to deal with the two capacitors that are in series, because we want to sort of take it from the area where it's more complicated and start to just break it down and make it more and more simple. So the equivalent of the two that are in series can be found by taking 1 over 0.3 plus 1 over 10. And if we do that math, we find that this is actually 3.43. And this, if we take the inverse of that, gives us equivalent capacitance of 0.29 microfarads. And so that means that what we've done is we've changed this combination of capacitors to look like now just two that are in parallel with each other, the 2.5 microfarads and the 0.29 microfarads. So you see where we've done that simplification. Now what we're going to do is we're going to, again, remember that what we have here now is these two that are in parallel to each other, 2.5 microfarads and 0.29 microfarads, which is equivalent to what we see here. And now these are two in parallel, so the equivalent is found by simply adding these. And we get 2.79 microfarads. And so now what we've done is we've changed this combination of three different capacitors into one capacitor with a capacitance of 2.79 microfarads. And that is how we use our rules to simplify a combination of capacitors. In class, we will go back and look at this and also look how we can go back and figure out the charge and voltage across each of the capacitors in our combination.